So let's go back to the beginning of the lesson. So what we learned so far is that we can find something called the antiderivative by going through a process called integration. I suggest you look back over this rule if you'd like and some of the problems that we worked on in class. It's like the reverse power rule. We'll practice it again today, but the most important thing that you should remember at this point is that each of these antiderivatives has a plus c at the end, that unknown constant. And what we're going to look at today is how we can find c sometimes. And so finding c, the constant of integration, we can find c when we are given an initial, let me not say initial, we are given a point that, a point like an x and y value, that the antiderivative, which I also call like kind of informally, I call it the original function, goes or passes through. The one thing that I want to highlight is there's a place in these problems that students often miss the last mark. And so it's a little remember, and we'll see it when we do some practices below. Remember. Rewrite entire function with c as your final step. You'll see what I'm talking about in the first example below. Okay, have your calculators out. I'm going to be asking you to end solve. And as always, I recommend you don't just trust that I have the answer, but you practice end solving, because as we know, sometimes we find that we make mistakes with end solving. The first question, I'm not going to review the antiderivative with you. I'm just going to go straight through it. So we're given f prime of x, that's the derivative, and we want to find the antiderivative, the specific one for what they call the boundary condition. This isn't quite IB terminology, but it's fine. It's basically we're given a point that the original function goes through. Notice this is the original function because it says f. I'm given the derivative, so I'm going to go ahead and find f by doing the process of the antiderivative. To do that, remember we write 50x again. Add 1 to the exponent. There's an exponent of 1. So if I add 1, I have 2. And divide by the new exponent. So I divide by 2. Remember the antiderivative of 25 is 25x. We talked about this last time. You can look back at the notes. And then remember we always have the plus c. Well, what today's lesson is we can find c. How can we find c? We can substitute 1 in everywhere we have an x, and we can substitute 60 in for the output. So set it equal to 60. And when we do that, we have 60 equals. I'm going to substitute 1 in for x. I'm actually going to also divide the 50 and the 2 right now, which gives me 25. And then I'm going to substitute 1 in for x, so that's 1 squared plus 25 times 1 plus c. You can end solve this if you'd like to, or you can solve this if you're confident with a little bit of algebra here. You can solve this without end solve, and you should get c equals 10. This is where I'm talking about students get really excited because they're like, oh, I found C. Yeah, I'm going to move on to the next part. But There's one final step because the question will always say find the actual antiderivative, which means you want the original function. And so you have to write this final step that the original function now is this here, but with the c substituted in. So we have that function, which was 50 over 2, or 25, x squared plus 25x plus 10. If you feel really good, you can try the next two, and that's the answer. If you feel really good, you can check the next two on your own and just check them, fast forward the video and see if you get the same. If you want to keep watching, you can also keep watching. The next one's a little bit trickier because of the variables. Notice it's written a little bit differently. I don't have a prime. I have dx dt. And I want to find x. The original function here is going to be x. We're used to seeing dy dx. When we have dy dx and we find the antiderivative is y equals something. Excuse me. This is a little bit different because x is actually going to be the name of the function that we're finding. And so I'm going to have x equals when I find the antiderivative. And by the way, this is the original point that I'll substitute in when I'm done to find c. So I'm going to have x equals, I'm going to copy down 10t to the third. Oh, no, not to the third, sorry. I'm going to add 1 to the exponent and divide by that new exponent. Oh, crap. I forgot. Oh, no. I forgot to rewrite it first. I'm going to rewrite it over here. How do I rewrite this? I have 10t to the third, and I'm going to rewrite 18 over t squared as plus 18t to the negative 2. That way, when I find the antiderivative, I can use that reverse power rule a little bit easier. I'm going to have 18t, add 1 to the exponent, negative 1, divide by the new exponent, negative 1, plus c. So yeah, I needed to rewrite that first. Sorry, I'm feeling a little under the weather today. All right, so we have x equals 10 divided by 4. I'm going to simplify this first. That's 5 over 2, t to the fourth. I'm just simplifying what I have. 18 divided by negative 1 is going to be negative 18, t to the negative 1 plus c. I want to find c. How am I going to find c? I'm going to plug 2 in everywhere I have a t, and I'm going to plug or substitute 46 in for the x, because that's what x is equal to, and that's what t was equal to 2. So I would always write this first. Don't just go to your calculator, because you get a mark for showing this step usually, showing that you knew to substitute this in. So you have 2 to the 4th power minus 18 times 2 to the negative 1 plus c. You can end solve this in your calculator, and when you end solve this, you should end up with c is equal to 15. Nice work. You're not done. Remember that the final step is to rewrite the final equation with the c in it. So I'm going to go back up here where I had x equals, and I'm going to substitute the c in for c. What I found for c in for c. T to the 4th minus 18 t to the negative 1 plus, not c, but what I found c was, which is 15. All right. That's the answer to that one. And the last question, it looks like a finance one. C here usually represents cost. We have the derivative. I want to go backwards and find regular c. Look here, I'm given the original point that it goes through to. Now, notice when I find the antiderivative, so c of n, add 1 to the exponent, so I have 100n, add 1 and divide by the new exponent, 100 over 3 is not going to simplify, so I'm going to leave it like that anyway. Minus 50n, add 1 to the exponent, divide by the new exponent, and the antiderivative of 120 is 120n. And I need a plus c. I'm not going to use the letter c here. It doesn't have to be a c. That's just what we call it sometimes. Why isn't it a good idea, or why is it a bad idea to use a c here? Because I'm already using c to represent cost. And so pick another letter. I'm just going to call it b, a different constant that I need to find here. You could use a c, maybe it'd be fine in an IB exam, but it'd get really confusing for you. So it's a better idea to use a different letter like b. Now I can substitute 9 in for my n. So everywhere I have an n, I'm going to substitute in 9. And then I'm going to set the whole equation equal to 355. That's the input and the output. And so I have 355 is equal to 100 times n to the third power over 3. I see I have 50 over 2 here. I'm going to go ahead and simplify that to 25. I can do 50 over 2 in my head is 25, but I still have n squared plus 120 times n plus b. And if I n solve this correctly, or if I did this correctly, I think you should get b equals, I hope I did, I got b equals negative 23,000. As always, you're not done. So we want to rewrite this original equation that we found, c of n, but with the constant of integration, that b substituted back in. So we have 100 n to the third power over 3 minus, I'm going to divide 50 in 2, so minus 25 n squared plus 120 n minus 23,000. And voila, you're finished.